All right, so Felix Klein, he had this quote. Mathematics, in general, is fundamentally the science of self-evident things.
Mm-hmm.
And, when you first hear it, it sounds simple enough, right?
Sure.
But then you start to dig a little deeper. You look at something like a function and what it actually does, how it transforms things. And then you think, okay, how do we go backward? How do we undo that process? How do we find the input that gave us the specific output? And suddenly it's not so self-evident anymore.
It's like you can't just hit rewind.
Yeah.
Especially when you're dealing with functions that have a kind of a repetitive nature.
Exactly.
Like our good friends, the trigonometric functions.
Yeah.
Trying to find their inverses, that's where things can get, well, a little tricky.
Absolutely. And that's exactly what we're diving into today, inverse trigonometric functions. So if you're listening, maybe you're prepping for a test, maybe you're working on a project that involves some mathematical modeling, or maybe you're just, curious about how these things work.
Yeah, always good to be curious.
We've got this document, lem102.pdf, that really gets into the nitty-gritty of these functions. Like, when do they even exist, and what are some of their quirks, their properties? Our mission today is to pull out the most important stuff from this document, to give you a solid understanding of why these inverse trig functions matter, how we define them, and some of the key relationships they have.
Because there are some really cool relationships, some really elegant symmetries.
Oh, yeah. And we'll definitely get into those. So think of us as your guides. We're going to navigate this sometimes dense but ultimately fascinating world of inverse trigonometry together.
So before we flip a sine or a cosine on its head, let's back up a bit. Let's talk about what it means for any function to have an inverse.
Right. Let's lay the foundation.
The source reminds us that for a function, let's call it f, to have a proper inverse, a true foe, it needs to be one-to-one. It's got to be injective. That means every input maps to a unique output. No two inputs can have the same output.
Right. No collisions allowed.
And it also needs to be onto or surjective. That means every possible output value actually gets hit by some input. There are no gaps in the range.
It's like a perfect match, right? Every input has its unique partner on the output side, and nothing on the output side is left out in the cold.
Perfect analogy. The source uses this notation. If we put in x and get out y through our function f, so y equals f of x, then the inverse function, let's call it g, takes that y and brings it right back to the original x. So g of y equals x. This g is what we call f inverse.
It's like an undo button. You apply the function, you get a result, you hit undo with the inverse function, and you're back where you started.
Exactly. And the document really emphasizes these core identities. F inverse composed with f applied to x just gives you back x. And f composed with f inverse applied to y gives you back y. These identities are saying that applying a function and then its inverse, or the inverse followed by the function, just cancels everything out. You end up right back where you started.
Okay, so that's our foundation. Now let's bring in the trigonometric functions. Sine, cosine, tangent, all those familiar faces.
Right. Our old friends from high school trigonometry.
And as our source points out, these standard trig functions over their entire natural domains, well, they don't quite fit that one-to-one and onto requirement.
They're a little too free-spirited for that. Let's take sine as an example. You can plug any real number into sine.
Yeah.
Right? That's its domain, all real numbers. But the outputs you get, the sine values, they always fall between -1 and 1.
Right, bounded.
And here's the issue. You can have multiple angles, multiple inputs that give you the exact same sine value. Think about it. The sine of 30 degrees, which is 6 radians, is 12. But the sine of 150 degrees, which is 5/6 radians, is also 12.
Ah, so we have a collision.
Exactly. And it's not just those two. You have infinitely many angles that all have a sine of 12. So sine isn't one-to-one over its entire domain. It's not a perfect match. Same goes for cosine. Its domain is all real numbers, and it's also bounded between -1 and 1.
So how do we fix this? How do we make these trigonometric functions invertible?
Well, we get a bit clever. Instead of trying to invert the function over its entire domain, we restrict it. We pick a smaller piece of the domain where the function does behave nicely, where it is one-to-one and onto.
So we're kind of like taming it. We're putting it in a smaller box where it can't misbehave.
That's a great way to put it. For sine, for example, if we restrict its domain to the interval from -2 to 2, something interesting happens. Within this interval, sine becomes one-to-one and onto. Every angle in this range has a unique sine value, and every sine value between -1 and 1 is produced by exactly one angle in this range.
So we've created that perfect match.
Exactly. And we could choose other intervals too, like from -3, 2 to -2, or from 2 to 3, 2. In each of these restricted domains, sine is invertible. But this leads to different branches of the inverse sine function, also known as arcsine or sin.
So depending on which interval we choose, we could have different versions of the inverse. That seems like it could get messy.
It could, which is why we have something called the principal value branch. For sine, this is the branch where the output, the angle, is always between -2 and 2. So when you see sinun -1, -2, 2, it means the inverse sine function takes a number between -1 and 1 and gives you a single unique angle between -2 and 2.
So it's like we've chosen the default branch, the
Yeah.
one we're going to use unless we specifically say otherwise.
Exactly. The principal value branch ensures that we have a consistent and unambiguous way to talk about the inverse sine.
Okay, so that's sine taken care of. What about cosine? How do we define its inverse and what's its principal value branch?
For cosine, we restrict its domain to the interval from 0 to metal, and its inverse, cosi or arcosine, has a principal value branch where the output is always between 0 and s, so cosi -1, 1/8 or more.
And what about tangent?
For tangent, we restrict its domain to the open interval from user 2 to 2. Its inverse, or air or arctangent, then has a principal value branch with a range from -2 to 2, not including those endpoints. So, 10 do 2, 2, 2, 2. Notice the parentheses instead of brackets, indicating that gazy 2 and 2 are not included in the range.
That makes sense since tangent goes to infinity at those angles. Okay, what about cotangent?
Cotangent is similar. We restrict its domain to the open interval from 0 to ba, and its inverse, co2 or arcotangent, has a principal value branch where the output is always between 0 and ham, not including 0 and s. So, codudu are 0.
And finally, second and cosecant. Those are always a bit trickier.
They are. For cosecant, we restrict its domain to mus2, excluding 0, and its inverse, cosecant or arcosecant, has a principal value branch with a range of mus2, also excluding 0. So cosecant are nominate 1 no, nonish 2, 2, 2 now. Notice that cosecant's domain and range exclude values between nisal 1 and 1 because it's the reciprocal of sine. And for secant, we restrict its domain to 0, excluding 2, and its inverse, secant or arcsecant, has a principal value branch with a range of 0, also excluding 2. So secant are nice 1, 1, 0, path 2. Just like cosecant, secant's domain and range also exclude the values between nice 1 and 1 because it's the reciprocal of cosine.
The source actually has a really helpful table summarizing all these domain restrictions and principal value branches for each inverse trig function. I think it'd be a good idea for our listeners to check that out.
Definitely. It's a good reference to have.
And while we're at it, there's another important point the source highlights that we should mention. Sin x is not the same thing as sin x.
Right, that's a common mistake.
The little winged one in the superscript. It means something different. In sin x, it indicates the inverse function, not the reciprocal. Sin x is just 1 over sin x, which is the same as cosecant. And the same applies to all the other trig functions.
So it's really important to pay attention to the notation. Absolutely. The source also reminds us that when we're talking about these inverse trig functions, and we don't specify a particular branch, we're always referring to the principal value branch. And the value we get from that principal branch is called the principal value of the function.
Got it. So principal value branch is our default setting. Okay, so now that we've got all our inverse trig functions defined and we understand this concept of the principal value branch, are there any useful relationships or properties we can use to simplify things?
Oh, absolutely. The source goes into quite a bit of detail about these properties. Let's start with property 1, which deals with reciprocal relationships. It says that sin 1x is equal to cosine x as long as the absolute value of x is greater than or equal to 1. Similarly, cosine 1x equals sin 1x for x of 1, and tan 1x equals coto x for x greater than 0.
So these are basically saying that if you have the inverse of a reciprocal, you can rewrite it as the inverse of the original function.
Exactly. These can be really handy when you're trying to simplify expressions. For example, if you have CDUR 2, you can rewrite it as cosio 12, since 2 is greater than 1.
Okay, that's neat. What about property 2?
Property 2 is about the inverse of negative arguments. It says that SODIR x is the same as SODIRIO for any x between nobens 1 and 1.
Yeah.
Similarly, tan x is the same as tan x for any real number x, and cosio x is the same as cosio x for any x with an absolute value greater than or equal to 1.
So for those three functions, if you have a negative argument inside the inverse, you can just pull the negative sign out.
Right, but it's a bit different for cosine, secant, and cotangent. Property 3 tells us that cosi x is actually equal to cogio x for any x between mogia 1 and 1. Similarly, CQX is equal to 2EX for any x with an absolute value greater than or equal to 1, and conear x is equal to conear x for any real number x.
Ah, so for these three, instead of just pulling the negative sign out, we have to subtract the inverse of the positive argument from Dex.
Exactly. It's a little quirk to keep in mind.
Okay, so we've got reciprocal relationships, and we've got how to deal with negative arguments. What's next?
Property 4 talks about the sum of an inverse trig function and its co-inverse. It says that sin x plus coq x always equals 2 for any x between -1 and 1. Similarly, the next plus coq x always equals 2 for any real number x plus sec x always equals 2 for any x with an absolute value greater than or equal to 1.
That's kind of elegant, isn't it?
It is. There's a nice symmetry there. And the source even gives us an example. Coq x plus coq x. Using property 4, we know that sec x plus coq x equals 2, and the cosine of 2 is 0. So cosec x plus cosec x equals 0.
Okay, that makes sense. What about property 5?
Property 5 gives us formulas for the sum and difference of arctangents. It says that tan of x plus tan is equal to tan of x plus y divided by 1 minus y, but only if x is less than 1. And tan of x minus tan is equal to tan of x minus y divided by 1 plus y, but only if x is greater than -1.
So these formulas let us combine two arctangents into a single arctangent.
Right. And these formulas can be derived from the tangent addition and subtraction formulas.
Cool. And finally, property 6.
Property 6 gives us something like double angle formulas, but for the inverse tangent. It says that 2 times tan x's can be expressed in 3 different ways, depending on the value of x. If the absolute value of x is less than or equal to 1, it's equal to sin, 2 by 1 plus x. If x is greater than or equal to 0, it's equal to co-0, 1 plus x 0. And if x is between -1 and 1, it's equal to tan 8, 2 by 1 x 0.
So we have different options for how to express 2 times tan x depending on the situation.
Right, and these formulas can be derived using a simple substitution, like letting x equal tan y.
It's interesting how all these inverse trig functions are like interconnected.
Yeah, there are a lot of elegant relationships there, and the source even mentions that these inverse trig functions and their properties play an important role in calculus. They help us define and solve certain integrals.
Right, they're not just theoretical curiosities, they actually have practical applications. The source also mentions that they're used in science and engineering.
Yeah, in fields like physics and electrical engineering, where you're dealing with things like waves and oscillations, these inverse trig functions come up all the time.
I always love learning about the history of math. The source mentions that a lot of the foundational work in trigonometry was actually done by ancient Indian mathematicians, people like Aryabhatta, Brahmagupta, Bhaskara.
It's amazing how far back these ideas go and how they were developed in different parts of the world.
Right. The source mentions that the Indian approach to trigonometry was actually more effective than the earlier Greek methods, and it was eventually adopted worldwide.
And they even introduced the sine function.
Yeah, that was a major development. And the notation we use today, like sin x and cosine x, that was suggested by Sir John F.W. Herschel, a British mathematician and astronomer.
It's interesting how these ideas have evolved over time and how different cultures have contributed to their development.
So, to sum things up for our listeners, we've gone on a journey through the world of inverse trigonometric functions. We started by talking about what it means for a function to have an inverse, and then we saw why our standard trigonometric functions needed a little bit of taming to become invertible.
We restricted their domains, and that allowed us to define their inverses.
Right. And we talked about the importance of choosing a principal value branch so that we have a consistent way to talk about these inverses.
And we explored some of the key properties of inverse trig functions, relationships that can help us simplify expressions and solve problems.
Hopefully you're feeling a lot more comfortable with these inverse trig functions now.
Yeah, they might seem a bit intimidating at first, but they're really not that bad once you get to know them.
And they're incredibly useful tools, not just in math, but in other fields too.
So as a final thought, now that you've seen how we can make trig functions invertible by restricting their domains, think about this. Are there other functions out there, maybe ones you've encountered in your own work or studies, where you might need to use a similar trick? Where you might need to restrict the domain to define an inverse?
It's a good question to ponder, and it might lead you to some interesting insights.
Because the idea of inverses and the conditions under which they exist, it's a fundamental concept in math. And it pops up in all sorts of unexpected places.
So keep exploring, keep asking questions, and who knows what mathematical discoveries you might make.
And most importantly, have fun with it.
Absolutely. Until next time.